That's great. Thank you so much, Ali. And thank you guys so much for your time and attention today. So I'm here with Karthikeyan and Shruti on my team who've been doing great work in Velox QDF, and we're just so happy to be part of this community. And we've made a lot of progress since last year. Really excited to talk about where we've come and where we're going next. So today, I know there's a lot of Spark content today and a lot of Presto content yesterday, but most of our integration efforts so far have started with Presto Velox. But of course, everything we're building in Velox QDF applies equally well to gluten, and we have a lot of internal results about that. But today, the focus we want to emphasize is the Presto execution on GPUs using Velox and Nvidia QDF. So if you're not sure, if you haven't heard about this integration, or you want to learn a little bit more about how it works, the right way to think about it, that's where I want to get started and introduce QDF a little bit for folks who haven't worked with it before. And then I want to go into Presto GPU performance. We've been looking at TPC benchmarks and scaling out on some GPU clusters as well to get up to 30K. We recently did in the last few weeks. And then I'm going to hand it over to Karthikeyan to talk about our development roadmap in Velox QDF. You've seen a lot of his work and the team's work in open source, and that's only gaining momentum. And then I'll hand it over to Shruti to update on where we are with TPC DS expansion, which has been our main focus this quarter. So yeah, we love Velox. Velox is great. This has been such a great partnership. Really kicked off in a strong way last year after VeloxCon last year. And Velox is great. And the open source community is a huge draw for us. QDF is open source as well. And we use open source building blocks for GPU execution. And all C++ execution, QDF's main APIs are C++ as well, so it's very easy to map these together. And the pluggability and extensibility of Velox is really part of what makes this possible. Like, you couldn't plug in a new executor if that wasn't a core part of what Velox wanted to do from the beginning. And then, that's the engine itself, but also in the way you deploy it and use it. Velox has broad goals for batch, ETL, interactive, the AI training offline and online pre-processing use cases. So Velox has invested a lot in the compatibility layers out to different front ends. And that's just a super valuable thing about the ecosystem and one of the best parts about the community. The deployments via Spark Gluten and Presto C++ have made huge progress. The migration updates we got yesterday from Meta and Uber, these are huge milestones. I mean, the pathway between 90 and 100% was awesome to learn about in detail. And these deployments are just make it such an attractive community, and we're delighted to be a part of it. Okay, so but what about QDF, and how does QDF fit into the story? So QDF is an open source CUDA C++ library for GPU data processing with C++, Python, and Java bindings that you can use to access the algorithms in QDF. And Velox QDF is it's in the experimental namespace in Velox. And we've got a driver adapter that lets you replace all the GPU operators, or all the CPU operators with GPU operators. And this is kind of an example here in the diagram. You'll get plans. The Velox worker will get plans in from the Presto coordinator or through Gluten. That's an executable pipeline in Velox, and we use the driver adapter to convert it into a GPU pipeline. And now we've got these QDF vectors that can point to data that remains on device, and we can do end-to-end GPU execution using this replacement model. And now, when you run Velox QDF, we run it a little differently than Velox is used to running. So it's pretty impressive that Velox is still able to execute well when we're running single driver or two drivers, where Velox is used to running with a driver per core, and bigger batch sizes as well. We don't want to process kilobytes of data per task. We want to process hundreds of megabytes or gigabytes per task. So, but Velox is flexible enough that this hasn't really been an issue yet. It hasn't required any special tuning really either. Velox QDF also extends the connectors because, as we know, like getting I/O right is critical. And we're able to keep some of the metadata processing for Iceberg, for instance, in the main Velox implementation, and just take the heavy compute parts like deletion vector processing and move that to GPU. So Velox has made a great framework to build in a GPU integration, really at the ground floor of the engine. All right, so I want to talk a little bit about the cuDF ecosystem and why Velox is so important for it. So if you look at the stack to like reach a runtime like Presto or Spark, and you want to try to accelerate that, you need some sort of compatibility layer to map down to a different way of running it that isn't the way it normally runs. You need an execution engine that's going to be in charge of using the resources to compute the plans, and you need operators to do each step of that, and those operators need to call algorithms. So go back 2 years ago, and Spark Rapids was the main way that distributed ETL could access GPU acceleration and cuDF. And Spark Rapids, it's open source, and all that code, they had to write their own operators, they had to write their own execution engine, they had to do all the Spark compatibility, and that kind of fits in this big Spark Rapids bubble here. And then we've done the similar work with Polars and DuckDB as well to like build up all the interface that you need for Polars, a Polars user to get access to cuDF for data framework, or a DuckDB user to get access to cuDF. But we haven't found a way to really reuse code that well between these stacks. But Velox has really changed that for us, because Velox gives us an execution engine that we can really separate the execution needs from the compatibility needs and reach Spark and Presto with the same operator. We write the operator once in Velox cuDF. It ties into the algorithms that we've been developing over years in the cuDF library, and then we can tie it into any Velox app from there. So Velox has been a really great tool, and we're really pivoting our efforts in cuDF to focus on that part of the ecosystem. And we've come a long way. So last year we talked about, we had just scrambled to get together a TPCH run through Velox as a pure Velox run at scale factor 100 last year. And since then, the first thing we were trying to do is, okay, well, running via Velox is great, but we need to really run through Presto or another distributed runtime. We targeted Presto first. And we got to start upping the scale factor. So by Tech Exchange last year, IBM Tech Exchange in October, we got the 1K run to go on a single GPU, and then a Presto worker doing the job, getting plans from the Presto coordinator, setting it up the right way. And then the big breakthrough happened this year with UCX Exchange to let us do multiple GPU workers communicating smoothly. And Marios is going to talk more about that later this morning. So it's a crucial feature here, because you need to have a fast shuffle tool to make these workers go smoothly together. If you take GPU workers and they have to use HTTP exchange, you can't get, they end up idle is what happens. So you need a fast shuffle to make this work. And yeah, so for GTC, we got a 3K run up on multi-GPU with 3, 4, 5, 6, 8 GPUs. And then recently, we've been scaling out on a cluster where we can go and do 10K and 30K. And I'm going to share more about that in the performance section. Plus, TPCH is great, but we need to get DS, and then we really need to get the next round of operators that are crucial for customer workloads. So that, I view these as early milestones in the real work in customer-facing workloads with their data types and data sources and UDFs and all of it. That's really the focus moving forward from here. But we have made great progress in this quarter on TPCS that we'll get to a bit later. Okay, so on the performance side, one way to zoom out on the ecosystem is to look at how Presto Java, Presto C++, and then the Presto GPU runners, the data that we're collecting regularly on these different modes of running Presto. So Presto Java to Presto C++, this gives, when we do this test in the cloud on small clusters at a TPCH 1K, we see the 5x speed up that folks at Meta and Uber have also kind of presented the same order of magnitude from their migrations. And this is great. And Presto Java has started its open source journey in the early 2010s and attracted a big community and has been really successful, and I think the whole Presto ecosystem is doing a great job pivoting over to native execution and getting big benefits from that. One of the things that's great about Presto C++ is it makes it much easier to tie in GPUs than it would be straight into Presto Java. That'd be a much harder thing to do. But with Velox, there's a good way to do it. So these numbers, we're showing more speedups going to GPU with A100s and B200s. Now I appreciate we moved from cloud to on-prem, and we need to be like, we need to talk about our data sources carefully here. But if you can get a hot cache run, the GPUs can really scream through, and there's more speedups to come. So to give a little bit more detail about the TPCH 1K and 3K picture, I have some CPU runs here with 8 nodes running versus a Lustre data source, and we're running it as hot as we can with the async data cache and soft affinity and discarding the first run and all that. And then I'm comparing it to a few different GPU counts running the same workload. Because we can run 1K on a DGX. A DGX has 8 GPUs on it. But you don't have to assign all of them to the job. So you can have 1 or 4 or 8 working on 1K together. And at 3K, we can have 3 GPUs or 6 or 8 GPUs on this DGX working together to complete the queries. And these speedups are in the 3 to 10x range, and yeah, we're kind of focused on running as hot as we can in both cases, here. So there's our internal resources are focused on on-prem testing, but we're really interested in extending this to the cloud as well, working on the P4 and P5 instances, and also the G7, G7E instances will be our main targets. Before our on-prem resources, we can also reach higher scale factors with a system that we're building out that we hope can be kind of a standard in what speed of light GPU data processing looks like. So NVL 72 GB 200 with IBM storage scale system. This is an on-prem system in our lab that we've built out, and it kind of eliminates the major bottlenecks that GPU data processing has with I/O and shuffle. And we want to make sure that this runs at speed of light and runs as well as it can. And you could imagine having the system servicing millions of queries, and just load balancing across the 72 GPUs on it. So you should think about this system not as like, instead of having a cluster of CPU, you'd have this like tightly integrated GPU cluster with really good, really high capacity storage that's super fast, and super fast connectivity between the GPUs and tons of compute available for data processing. So a few of these NVL 72 pods could service a huge query load is the kind of the idea that we're working towards. So we're bringing this up. We brought up the system just in the last 2 months, and this is the first results to come off of it at 10K and 30K. So we're running in 2 to 3 minutes at 10K depending on the GPU count, and about 5 minutes at 30K for 24, 28, 32 GPUs. And then there's some overlap with at 10K, we can run it either on the DGX, which is like a single node, it's kind of like a P5 instance that you can get on AWS. You can run up to 10K on the single node, and you can also run that on 8 GPUs on the cluster as well. So it's taken a lot of work to stand up the storage scale system and have it work smoothly with Velox. But basically everything you need to run this comes in the open source now with UCX Exchange, and to get the storage to run well, you need a GPU direct storage, so you can directly send data RDMA into the GPU memory from the storage cluster. And we have a blog post coming out about the storage and I/O side, that the setup that works really well, and what we encourage folks to use. And if you're interested in doing testing on the system, we want to publish a reference architecture about this NVL 72 and storage scale system. So the email here, dalinfo@Nvidia. We're looking for, we have a few partner slots available to do development and workloads on the system and make sure it works as we're designing it to. So yeah, this is part of where we're going with Presto GPUs on the performance front. And from here, I want to really, this is VeloxCon. We need to go back to Velox for a bit and talk about what's been happening on mainline, what we have in open PRs, and what's coming next. So I'm going to hand it to Karthikeyan.
Thank you, Greg. So yeah, let's transition to discuss about the Velox QDF project update and our roadmap. So over the past year, we have transformed this from an experimental module to complete true powerhouse, and I'm excited to share the progress with you. Yeah. So first and foremost, I want to emphasize that Nvidia is fully committed on the open source development, right in the Velox's main branch. So everything we do is built in the open. QDF library is built in the open, and Velox QDF is also built in the open. To give you an idea of our momentum, so last year at VeloxCon 2025, the Velox QDF amounted for less than 1% of the pull requests. Fast forward to today, more than 10% of the pull requests, monthly pull requests, are coming from Velox QDF. And that's an incredible momentum due to the open source community. And we have made big improvements in functionality in Velox QDF. We have made huge improvements in Velox's CA infrastructure. So we're enabling dedicated GPU builds and GPU unit tests, and first tests are coming. So we have to give big thanks to our partners at Meta and IBM who made the continuous integration possible. So their help in setting up continuous integration in Velox QDF helped any contributor to develop and test their code before committing to the Velox. And next, because of this, we have had a lot of contributions from the community. And IBM research has actually already merged the UCX exchange, which allows shuffle between the GPUs using Nvidia NVLink. Okay. Let's look at the code architecture here. So we have Velox, massive Velox code base with more than 640,000 lines of code, which has connectors, CPU operators, and then expressions. On the right, we have QDF with GPU data structures, algorithms, and GPU readers and writers, amounting to more than 190,000 lines of code. So in between sits the lean critical bridge, Velox QDF, with only 18,000 lines of code. This bridges the gap between these two massive code bases and brings GPU acceleration natively to Velox. Let's see what we have achieved with this architecture. So today, we have successfully GPU accelerated 34% of the GPU operators, of the Velox core operators, and 37% of the data types. We heavily focused on fixed width data types, string data types, and we are currently near completion for full decimal support, which is critical for financial workloads. And we also support list and struct data types. So for the expression, we have added a lot of functionality to the expression evaluation. So currently, for Presto and scalar functions, we support 19 scalar functions and 6 aggregate functions. And Windows aggregation is currently actively worked on with the open PR right now in the Velox. And we have made massive changes to expression evaluator. And we made it this made it easy to add any new functions to expression evaluator, which sparked a lot of amazing community contributions. And none of this is not possible without the amazing community. So we have merged over the past year more than 250 PRs and with 60 issues. This incredible momentum was possible with more than 20 contributors from Nvidia, Meta, and IBM. And to all those super cool developers in the audience and watching video today, thank you. You are the reason for this incredible momentum. And let's go and look at the next Velox QDF roadmap. So going forward, stability is our #1 priority. So now we have the Velox's CA for GPU, which runs dedicated GPU builds and unit tests. Every commit to the Velox QDF module is actually verified before it gets committed. And we have new features coming up for operators, aggregations, and expressions. For operators, we will be adding more and more features for the joins, and we will be adding support for the window operator. And for aggregations, we are improving the streaming aggregation so that it can handle even more higher memory workload. And for the expression engine, we'll be expanding our coverage from like 19 functions, 19 plus 6 functions to more than 100 functions soon. And Velox has this massive fuzzers, incredible fuzzing infrastructure that tests different parts of the Velox modules. So we'll be expanding that to Velox QDF also, starting with joins. And right now, our partners, anybody who wants to start with Velox QDF has to build QDF from source, and that takes significant amount of runtime. So we will be releasing a QDF tarball with full support from NVIDIA Enterprise, so that it can be built from the binary. So stay tuned for that. Now, to go into detail about expression evaluator, so Velox QDF has 3 evaluators. One is AST, abstract syntax tree, then JIT, just-in-time compilation, and function evaluator. Function evaluator runs everything on each and every expression in an individual kernel. Now, QDF has this fused kernel called abstract syntax tree, which can support simple expressions in a single fused kernel. Whatever the expression that is not supported, we can do some pre-compute on the function evaluator and pass the overall results back to the AST evaluator, and AST evaluator can do a full expression tree on the GPU in a single fused kernel. The same, whatever we can execute in the AST in a fused kernel, we can do it with JIT, just-in-time compilation also. And we'll be expanding more on JIT function coverage. Next, for the FUX testing, to make sure that we have a reliable and then a robust Velox QDF, we want to expand whatever the Velox already has on fuzzers. So they have join fuzzers, expression aggregation. So we want to, we already have an open PR for adding join fuzzer, and we will be adding more fuzzers on expressions, then aggregations, then windows, then once we have GPU memory management and then spilling enabled, we'll have memory and spill fuzzers also. Now coming to the I/O part, we have an incredible announcement here for the I/O side. We will be adding Iceberg support to Velox QDF. So we are adding QDF Iceberg connector and a data source, which will enable Iceberg v3 support. And this QDF Iceberg connector offloads all the heavy lifting to the GPU side, like reading Parquet files, reading and applying deletion vectors into the QDF algorithms in the GPU, and also schema evaluation. The core the metadata processing is still handled by the Velox core code base. So this will enable overall Iceberg support in Velox QDF module. That's all for the Velox QDF roadmap. Thank you for keeping up the incredible momentum. If you want to contribute, open up a PR with that QDF in the title. And if you find a feature is missing for you to test or Velox QDF, just open up an issue. Our amazing contributors will take care of it. Thank you so much for your attention. I'll hand over to Shruti to talk about the incredible TPCDS progress.
Thanks, Karthikeyan. I'm going to be talking about our journey into TPCDS support, the features that we've added so that we can GPU accelerate this benchmark, and I will show us our performance story so far. TPCDS is another popular benchmark for measuring performance of query processing engines. Compared to TPCH, TPCDS has more complex queries because it has a dimension modeling approach where queries rely on information from fact tables and dimension tables, and therefore it results in more complex query plans. It also has more input tables. TPCH has 8, while TPCDS has 24 tables and has more queries as well. To GPU accelerate TPCDS, we have introduced new operators window, nested loop join, hash join operators, and this progress has been incredible, and we thank our contributors at IBM to help us make this progress. Another advantage of ensuring that we are entirely GPU accelerating this benchmark is that we can now ensure that there is very little data transfer between host and device, and we don't have to rely on CPU fallback for operators. Even lightweight operators like, say, group ID, which since we have now accelerated on GPU, ensures that we don't have to do this back and forth between host and device. The pie chart on the right shows some of the new operators that we've added and the amount of runtime it takes for TPC-DS SF100. If you look at one of these, that is Kuriev filter project, it is quite significant because for TPC-DS, it requires decimal support, that is, operands that operate on decimal type inputs. Velox Kuriev now has comprehensive coverage for decimal inputs. We have decimal 64 and decimal 128 support, and which for arithmetic operators, comparison operators, and aggregators. The operands, if they are of different scales, we have support for automatic scaling alignment. And we also have custom GPU kernels for decimal division, since we need to match Velox semantics of half-up rounding. We similarly have expanded support for inequality comparisons with decimal input signatures. For decimal aggregations, we again have custom kernels for the sum and sum and average aggregations over group by and global inputs by ensuring that we are storing our intermediate partial states, aggregation states, in a serialized format. The kernels are able to serialize and deserialize from the state to the serialized format. Now, all of this progress has helped us run TPC-DS for SF100 and SF1K. So this bar plot here shows the query runtime for these benchmarks on two different test environments. Presto CPU, where we ran a single worker, and this is on a single node, on a machine with 2 terabyte system memory with 220 cores. Our Presto GPU run is, again, with a single worker on a B200 GPU. For both of these runs, we are using local repartitioned Parquet files as data sources. And what we see is that for SF100, when we compare Presto CPU to GPU, we get about 5x speed up over all 90, and this is across all 99 queries put together. Moving to SF1K, we again see a similar 5x speed up with Presto GPU running in around 350 seconds for 98 out of the 99 queries. The one missing query is, maybe I can talk about that a little. It's query 23. And one of the reasons that it's failing is because there is an exploding join. And this is an issue that we are likely to face as we move to higher scale factors, is how are we going to tackle memory management on device efficiently? With these results have been possible because of all of the ongoing work in terms of open PRs in Velox. We have support for all the operators that I mentioned earlier, support for ensuring correctness for TPC-DS, and various optimizations that we needed to ensure that we are using device memory efficiently. The runs here have been with a staging branch that simply aggregates a lot of the open work that contributors have taken the time to put in. With this, I would love to welcome developers to contribute to Velox CodeF. Please do check out our issues on GitHub. They are tagged under CodeF. Also do reach out to us on the Meta Slack, say hi. We'd love to learn more about your workloads and what features you're interested in being accelerated on GPU. As Greg mentioned earlier, we are also interested in partnering on the NVL72 machine. So please do reach out on dialinfo, the email ID dialinfo. We have a deployment repo that is Velox testing, where that will help you deploy single worker and multi-worker Presto CPU and GPU. And do try it out with Velox and Presto with GPU acceleration. The link to the repo is on the slide here. We didn't get a chance to talk a lot about Spark Gluten integrations, but that's something that we are very interested in, and that is also under active development. With that, we come to the end, and we're happy to take questions.